Hi ladies, I'm not feeling too great today, so I'm going to record this lecture. And in class you will watch and listen to it and take notes as you go, and then we can review the material together next time. Today we're going to be talking about standing waves and something called the Doppler effect. So take a moment to observe the wave on the screen, and if you can, imagine that I'm on this end and maybe a pole is on this end. So it's like the spring in our classroom, right? As I create a wave, it kind of creates this interference pattern. Because as I shake this spring on this end, with a fairly low frequency based on this wave, I send out a pulse of energy that's traveling this way, and it gets reflected off the pole, comes back, moves forward, moves back, and so there's this interference pattern occurring between the waves that I'm producing and the waves that are being reflected off of this pole. Hopefully you also notice that this is a transverse wave with the particles of the medium moving perpendicularly to the energy transfer. So some other things that you can notice are these little red dots. So these areas of the wave where the slinky or the rope or whatever it is that we're working with aren't actually moving. Whereas there's other parts of the slinky or the rope that continually switch off between crests and troughs. I'll be bringing those up again in just a moment. All right, so what is a standing wave? We just saw an example of one. A standing wave is essentially any wave between 2 points. We can define it as a vibrational pattern created by 2 points, between 2 points, where the reflected waves interfere with the incident waves. So the incident waves are the waves that are produced by the source. So here by this little guy, as he produces the incident waves, the reflected waves interfere with those incident waves. So an example, like I said, of a standing wave would be a rope tied to a pole or a spring tied to a pole. Something along those lines. However, we can also use standing waves in harmonics once we get into sound. Now, in a standing wave, as I pointed out, there's certain areas that remain in equilibrium. So for instance, right now my mouse is on something called a node. Now the nodes are points of continuous destructive interference, and those points never actually move away from equilibrium. So on this wave, we can see that there are 5 nodes that never actually increase or decrease in amplitude. So node, node, node. And we see other regions of the standing wave that move up and down between crest and trough. These are called the antinodes. So if you can, imagine this is our spring in the classroom. You guys are welcome to mess around with it today. This individual is probably vibrating the spring at a pretty low frequency, and I'm inferring that because of this long wavelength. So based on this frequency, this standing wave has 1 node. What do you think would happen if they were to increase the frequency at which they were vibrating the wave or sending out that pulse? Okay. Since I can't do a demo myself, I did find a little video that we can watch. We're just going to watch about a minute of this guy creating a standing wave. And I am going to speed him up just a bit.
It's going to pump up and down at whatever frequency I set this guy to. When this guy pumps up and down, well, he sends a wave. He sends a wave down to this end, the wave reflects, comes back. Now, if I set it to just any old frequency, let me just turn this on. Well, let's go higher. So it's sending waves back and forth, but these waves are out of sync, if you like.
So I'm going to pause it real quick right there. Notice at the frequency that he set it to, the incident wave and the reflected wave are out of sync. So destructive interference is preventing us from seeing any major crests or troughs.
They're not exhibiting consistently constructive or destructive interference at any one point. But if I set it here, for example, I have what's called a standing wave. That is, the wave that's sent down and reflects constructively interferes with the next wave that comes down right at this point. Now the waves that come down and reflect, destructively interfere with the incoming waves right here, and that's called a node. I can touch it, and it still is working. So the node is not moving. Here it's moving up and down, and here it's moving up and down. And we'll see that in a second with the high-speed camera.
Okay, so that's pretty cool. That's actually his high-speed camera. But that gives you a little more insight into the nodes and the antinodes. Now, if he changes the frequency, then we end up seeing either more or less waves in that same amount of space, and I'll go back to it in just a moment. Now, like we saw, waves can either be in phase or out of phase. So if a standing wave is in phase, that means that the incident wave and the reflected waves are constructively interfering at certain points, and so we end up seeing, well, essentially just seeing this. We can see clearly the antinodes moving up and down. Whereas if a standing wave is out of phase, that's what we saw at the very beginning, where it was neither consistently constructively or destructively interfering, and it ends up kind of, you know, being a little bit out of sync or out of whack if you saw me doing it with the spring. And so at any given point, we're witnessing mostly destructive interference that is canceling out the amplitude of that wave. So that's out of phase. And as we know before, shaking the rope at different frequencies causes different standing waves because that produces different wavelengths. So in this image, right, he's shaking at a very low frequency, and so we actually only end up seeing one wavelength in this image. If we increase the frequency a bit, oh, I'm sorry, we only see half a wavelength in this image. But if we increase the frequency a bit, we can fit a whole wavelength in, and if we increase the frequency even more, we get 1.5 wavelengths in. So let me see if we can get that real quick.
So here we have what's called the second harmonic. It's the second possibility for a standing wave.
Skip ahead.
That's held at both ends. Because notice this is a node in the middle of it. We have 3 nodes for this wave. Now, like I said, second harmonic, well, what's the first one? The first one will be half this number, so 8.5.
All right, so there he decreased the frequency. And here we see the effect of increase in frequency. So now we actually have 1.5 full wavelengths. Sorry for talking over him. Trying to kind of get through this for you guys. Let's see. Okay, so here I ask, is it possible for one wave to cancel out another wave so that the amplitude is 0? If so, when do you think so? Hopefully you got that when destructive interference occurs between the incident and reflected waves. So when these two are out of phase. All right, so let's think about this. If we set up a standing wave with 3 segments, or 1.5 wavelengths as shown here, what do you think would happen if we were to increase the frequency by 2? How many wavelengths would we see? Well, if we double the frequency, we know that we half the wavelength, and so then in the same amount of space, we get twice as many waves. So if we were to double the frequency, then instead of getting 1.5 wavelengths, we actually get 3 full wavelengths. Okay, moving on from standing waves, we're going to talk briefly about the Doppler effect. So I'm going to bother you for a second with a siren. Okay. Now, pause the video for a second and discuss either with your neighbor or think about it for yourself what happened to the sound as the fire truck was approaching this filmer and then as the fire truck moved away from the filmer. What you just witnessed is the Doppler effect. And the Doppler effect is the apparent change in frequency of waves as you move toward or away from the source. So maybe you're familiar with the fact that as a siren, like a police car or a fire truck, as they're approaching you, you hear this very high frequency sound, whereas as they leave you, you hear kind of like a lower pitch or a lower frequency sound. So this is the Doppler effect. It's the apparent change in frequency of waves as you either move towards the source or away from the source. Now it's important to realize that the frequency coming from the source stays the same. So for instance, that fire truck is producing the same sound no matter where it is. The siren is the same, the sound waves that are coming off of the siren remain the same. However, based on whether you're getting closer to it or getting further from it, the frequency of the sound waves that you hear or observe is different. So we can imagine it like a little stationary bug in the water, right? Like if the bug is just sitting there and bobbing up and down, then it's producing these transverse ripples in the water. And we can measure frequency by measuring wavelength, right? So all of these waves have the same wavelength, therefore the same frequency. But if the bug starts to move this way, it actually catches up to the waves that it's already produced. And so these waves have a higher frequency than the waves moving away from him. The bug is still producing waves of the same frequency, but what's actually getting received or emitted is a higher frequency as he moves in this direction and a lower frequency as he moves away from that direction. We see a great application of this with sirens and horns. So if a siren is moving towards you, it's catching up to its own sound waves, and so you hear a higher frequency because they're closer together. But as it moves away from you, you end up hearing more of the original frequency that's emitted from that siren, and so it's a little bit of a lower pitch. The Doppler effect is useful for many reasons. So we can use the Doppler effect in Doppler radar and then also in police cars' radar guns. So we can send out a signal and have it bounce back to us, and it allows us to determine, like, A, whether the storm is moving towards or away from us, and then also we can find out how quickly it's moving towards us, for instance, if policemen are using Doppler radar guns, they can actually measure how quickly you're approaching them or what your car's velocity is based on the frequency of waves that come back from that source. So we'll talk a little bit more about that next time. I did want to show you a quick video. If I do get cut off, I have a 15-minute limit on this video. If I do get cut off, your homework is problem set 3. But if any of you guys watch The Big Bang Theory, Sheldon graciously dressed up as the Doppler Effect for Halloween.
Hey Sheldon, there's something I want to talk to you about before we go to the park.
I don't care if anybody gets it. I'm going as the Doppler Effect.
No, it's not.
If I have to, I can demonstrate. So what time does the costume parade start?
The parade?
Yeah, so the judges can give out the prizes for best costume. Most frightening, most authentic, most accurate visualization of a scientific principle.
Oh, Sheldon, I'm sorry, but there aren't going to be any parades or judges or prizes.
This party is just going to suck.
Oh, come on, it's going to be fun, and you all look great. I mean, look at you, Thor, and oh, Peter Pan, that's so cute.
Actually, Penny, he's not Peter Pan!
I got a handful of pixie dust with your name on it.
No, you don't. I hate what Sheldon's supposed to be.
Oh, he's the Doppler effect.
Yes, it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oh, sure, I see it now, the Doppler effect. All right, I got a shower. You guys, make yourselves comfortable.
Okay.
See? People get it.